Welcome to Fundamentals of Artificial Intelligence. Within knowledge representation and reasoning, we have looked at first order logic, resolution as an inference mechanism, resolution refutation proofs, and answer extraction. Having looked at resolution refutation proofs and the success we have had with resolution derivations, one should not be misled into thinking that resolution provides a effective reasoning paradigm within first order logic. One needs to remember that entailment in first order logic is semi-decidable. That is, algorithms exist that can say yes for every entail sentence, but no algorithms exist that can say no for every non-entail sentences. Resolution is refutation complete. That is, for an unsatisfiable set of clauses, some branch would contain the empty clause. A breadth-first search is guaranteed to show that the clause set is unsatisfiable. However, for a set of satisfiable clauses, the search may or may not terminate. For many applications in resolution, one is interested in having derivations where it would be possible to eliminate unnecessary steps. This is what is done through certain strategies and simplifications, which are refinement of the resolution process. We will wind up our discussion on knowledge representation and reasoning, looking at such strategies and simplifications. We start our discussion with looking at an infinite resolution branch. Here is a small example. Let us suppose our knowledge base consists of a single formula. Here, this formula is showing that the relation R is transitive. One could think of R as a relation that defines relative. So, Rxy could mean x is the relative of y. Now, if x is a relative of y and y is a relative of z, then we know x is a relative of z. That is the rule in our knowledge base. Let us now look for the existence of someone for everyone who is not a relative. That is, let us have a query like there exists an x for all y, not R of x comma y. Now, to remind ourselves, we will negate the goal and convert it into clausal form. So, if you look at the clausal form here and the only available rule, you could see that the knowledge base does not entail the query nor its negation. So, a resolution should fail. Problem is, if we pose it as a resolution, we end up generating an infinite sequence. We never get to the empty clause. So, let us look at the resolution derivation. So, here are my clauses, one that comes from the rule in the knowledge base and the other that is the negation of the goal. We have a substitution fx for y and that resolves into the resultant that is here. Now, if we resolve this further, we get an expression which says R of y of f of y. One step further, resolving it, we will have a disjunction, and when this disjunction is resolved further, remember there are only two clauses in the data set to start with. So, when it is resolved again to the negation of the goal, I have an expression which is now r of y of f of f of f of y. So, if you take a minute and focus your attention on these two subsequent clauses that we have obtained, the resolvents that we have obtained, you could see that after every second step, this would keep on repeating. And this suggests that we cannot use a depth first procedure to look for the empty clause. We may get stuck on such an infinite branch. Question is there a way to detect when we are on such a branch so that we can give up and look for alternate ways to the empty clause? Unfortunately, the answer is no. We are not in a position to say which of this path will take us to the empty clause and when we should give up looking for an empty clause in a given path. For first order logic, there is no way to detect if a branch will continue indefinitely. Now, this is because first order logic, one needs to realize, is a very powerful language. In fact, it can be used as a full programming language. Therefore, just as there is no way to detect when a program is looping, there is no way to detect if a branch will continue indefinitely. This is quite problematic from a knowledge representation perspective. There are no procedures that given a set of clauses returns satisfiable when the clauses are satisfiable. Resolution, however, is refutation complete. That is, it returns an empty clause if the set of clauses is unsatisfiable. And when clauses are satisfiable, the search, as I had mentioned before, may or may not terminate. Now, that is why resolution is not a panacea. Resolution does not provide a general effective solution to the reasoning problem in first order logic. Decision on which two clauses to resolve, that is, which resolution to perform, are made by the control strategy. Now, determining the satisfiability of clauses may simply be too difficult computationally. So, we need to consider refinements to resolution to help improve search. One option is to explore a way to search for derivations that somehow eliminate unnecessary steps as much as possible. And that is what we will focus on today. Look for strategies that can be used to improve the search in this sense. In fact, the most important way of avoiding unnecessary search in first order derivation is to keep the search as general as possible, and this is achieved in the unification step by taking help of what is called the most general unifier. So, we are looking for substitutions that are not overly specific. The substitution need to unify without making an arbitrary choice that may preclude a path to the empty clause. A substitution that we are looking for is through the most general unifier. We can limit resolution to most general unifiers without loss of completeness. Now, let us recall what we meant by most general unifiers. When there exists multiple possible unifiers for an expression E, there is at least one called the most general unifier, which is G here, that has the property that if S is any unifier for E yielding ES, then there exists a substitution S prime such that ES is equal to EG of S prime, and then G is said to be the most general unifier. Let us take an example to understand this. So, here are two expressions P a comma x and P y comma z. Now, if you are looking for an unifier here, then A for y and X for Z is a most general unifier. This is because I can always have a substitution S prime which is B for X, and then we get S which is A for Y, B for X and B for Z. Now, if we apply G and then apply the second substitution S prime, we will get the substitution S. Note that the reverse would not be possible, and therefore G is called the most general unifier. Now, when I have a most general unifier, the most general unifier preserves as much generality as possible for a pair of formulas. And using a most general unifier, we are actually leaving maximum flexibility for the resolvent to resolve with other clauses. So, the idea is that having a general search would lead me to the empty clause. One needs to, however, remember that the most general unifier is not necessarily unique. The most general unifiers helps immensely in search, as it dramatically reduces the number of resolvents that can be inferred from two input clauses. Now, there exist procedures including linear time algorithms for efficient computation of most general unifiers for a pair of literals. Most general unifiers greatly reduce the search and also can be calculated efficiently. Consequently, all resolution based systems that have been implemented to date use the most general unifiers. Let us now focus on the control strategies that could be used for better search during resolution. So, the first of them that we will look at is the breadth first strategy. Now, the breadth first strategy is complete, but is grossly inefficient. We would then look at a strategy called the set of support strategy. The set of support strategy have the flavor of a backward reasoning step, and we will see that it explores or it generates less number of resolvents. The unit preference strategy is actually an ordering strategy, and it selects a single literal clause to be a parent and takes a very interesting decision on which clauses to resolve next. The linear input form strategy that we will discuss next is one in which at least one parent belongs to the base set. Then we will look at a strategy called the ancestry filtered form strategy, where the parent is either in the base set or is an ancestor of the other parent. We will then mention about a couple of combination strategies. Let us take an illustrative example to understand these strategies. Now, this illustrative example is a worked out example from the book by Nielsen on Principles of AI, chapter 5, pages 162 to 163. These are the sentences. Number 1, whoever can read is literate. Dolphins are not literate. Some dolphins are intelligent. We need to prove some who are intelligent cannot read. Let us first make our choice of predicates. So, I have a predicate Rx to say X can read, a predicate Lx, X is literate, D of X, X is a dolphin, I of X, X is intelligent. Now, whoever can read is literate. I could write this first order sentence for all x, Rx implies Lx, and here is the clausal form of that sentence, not of Rx or Lx. The next statement is dolphins are not literate. So, this could be written as for all x, dolphin x implies not literate x, and the clausal form is not dx or not lx. Now, in order to keep the variables different in all the clauses, I would write not of dy or not of ly. Some dolphins are intelligent is written as there is an x, dolphin x and intelligent x. Now, the clausal normal form of this would be that I would introduce a Skolem constant a, and there is a conjunction and. So, I would have two clauses dA and IA. Some who are intelligent cannot read, that is the goal. So, we have the goal here saying there exists an x, intelligent and not read. Now, in order to prove this using resolution refutation, I would take the negation of the goal, which is not there exists x, I of x and not R of x, and I would finally end up having the clausal form not I of z or R of z. So, we have 5 clauses, and now let us look at the refutation proof for this. So, here are my clauses. I then start with resolving from the Gold-Well form formula itself, the clause that's come because of the negation of the goal, and I have R of A that resolves with this clause here to give me L of A, which then can be resolved with the clause not dy or not ly to give me not d of A. And now, once I have not d of A and d of A in my original clauses, I have the empty clause, and therefore, the statement is proved. Now, with this illustrative example, let us try to look at the different strategies that we have identified for discussion here today, and try to understand how does one arrive at the empty clause in each of the strategies. Now, one needs to realize when I am using this proof that the proof of this example had taken me from the original clause to the first level resolvents, to the second level resolvents. I generated the third level resolvents, and I got my empty clause only at the fourth level. Let us now look at the breadth first strategy. In breadth first strategy, all of the first level resolvents are computed first, then the second level resolvents are computed, thereafter the third level, and so on and so forth. A first level resolvent is one between two clauses in the base set. In fact, I define something like the ith level resolvent. An ith level resolvent is one whose deepest parents is an I minus 1th level resolvent. So, the breadth first strategy is complete, but is grossly inefficient. Now, one needs to understand that when I say a control strategy for a refutation system is complete, it is in the sense that its use results in a procedure that will find a contradiction whenever one exists. So, let us take our original problem with this 5 clauses and look for the empty clause, but while doing so, we would love to generate all of the resolvents at every level. So, we first have the original clauses, we resolve them to generate our first level resolvents. So, here are our 4 first level resolvents. IA resolve with not of IZ or RZ. So, I have an RA. Then here I have a complementary pair Rz and not Rx. So, I could resolve them, resolve this and this to generate my second resolvent at the first level. I generate my third resolvent at the first level and my fourth resolvent. So, I have my first level resolvents. Once I have generated the first level resolvents, I then try to resolve these with other clauses in the knowledge base and get my second level resolvents as marked here. So, one thing that needs to be noticed here is that for each of the resolution that I am performing, at least one parent is from the first level resolvent set. So, these are my second level resolvents. And then once I have my second level resolvents, I start generating my third level resolvents. So, one interesting thing that now we can notice is that I get an empty clause in a breadth first search in the third level resolvent set itself. Whereas, if you remember in the proof of the illustrative example, the refutation tree that I had to at least move to the fourth level resolvent to get to the empty clause. Next, let us focus our attention on another of the strategies called the set of support strategy. Now, a set of support refutation is one in which at least one parent of each resolvent is selected among the clauses which result from the negation of the goal well formed formula or from their descendants. So, in fact, it has the flavor of a backward reasoning step, because you are resolving with clauses that results from the goal well formed formula or from descendants of the goal well formed formula. So, each of the resolvents might actually correspond to a sub goal. Let us look at set of support in our illustrative example and the 5 clauses. Now, in set of support, I should resolve using clauses that results from negation of the goal well formed formula or its descendants. So, I have to start resolving from this, which is the negation of my goal. So, in the original clause set, I start resolving from there and resolve with I of A to get R of A. Now, the next is that this statement, which is a descendant of the goal well formed formula's resolution step, is to be used, or the goal well formed formula itself could be used. So, I take the goal well formed formula and resolve with its second possibility here, and then I resolve R A with not of R x or L x. So, I have an L A. Now, I resolve this descendant that has come from the goal well formed formula with a clause from the original clause set and have not of I y or not of d y, and then I could resolve this with the original clause set to have L A. I have my second level resolvents, and then I can think of generating my third level resolvents, which is not of d A. Now, one thing to observe here is that in the breadth first strategy that I had shown immediately before this, we had arrived at the empty clause while we were generating our third level resolvents. But the set of support strategy was unable to get to the empty clause in its third level resolution. So, third level resolvents do not generate, in this case, the empty clause in contrast to the breadth first strategy. So, let us see which was the path taken by my initial proof of the illustrative example. So, the darkened edges are the one which have been a part of the initial refutation proof. Now, if you focus your attention only on the set of support and the proof that I have obtained, you can see that the set of support produced the empty clause at the 4th level, was unable to get to the empty clause at the 3rd level for this problem. However, it did produce fewer clauses at each level than the unconstrained breadth-first strategy. Now, let us look at an ordering strategy. Like, well, I was looking for the modification of the set of support. Instead of filling out each level in breadth-first fashion, what if one could try and select a single literal clause, that is a unit, to be apparent in a resolution. Every time such units are used, resolvents would have fewer literals than do their other parents. So, using a unit clause together with a clause of length k would always produce a clause of length k minus 1, and then you could focus the search towards producing the empty clause. So, the original refutation tree that has been produced for this illustrative example has the flavor of unit preference strategy. Let us select a unit literal clause first. So, it could be my IA, that is a single literal clause, a single unit. You resolve it the complementary at this point and generate R of A. R of A is again a unit. So, you select R of A and resolve with its complement in this clause. So, you have L of A, you resolve with this clause which is a complement of L of A, and you arrive at a dA. Now, dA also is a single literal clause, and in the base set you have a dA, and you could arrive at the empty clause. Now, the unit preference strategy, every time the units are used, you could see that the resolvents have fewer literals than do their other parents. And by just having an order on which clause to select and making a very interesting rule that you will select only the single literal clauses could take me to the empty clause without generating number of clauses as was required in breadth first or set of support. The next strategy that is our focus here is the linear input form strategy. The linear input form strategy is one in which each resolvent has at least one parent belonging to the base set. The first level resolvents therefore are same as a breadth first search. At subsequent levels, a linear input form strategy does reduce the number of clauses produced. Now, one interesting thing to note about linear input form strategies are that they are not complete, like in the sense the breadth first strategy is complete. So, here are my clauses from the illustrative example, and let us try a linear input form strategy here. Recall that the first level resolvents, because everything is in the base clause, I will generate as good as the breadth first strategy. But thereafter, I would generate fewer clauses because I would have to have parents which are in the base set. So, I take R, and here is a clause in the base set that has a complement of R. So, I have L of A. Thereafter, I have I of Z or L of Z, and I look for a complement which is I of A in the base set. So, I have my second level resolvent. Here there is a complement of L in the base set. So, I have not of I or not of dz, and here I have a complement of R. Here is not R and here is R. So, I would have here not of I y or not of dy. So, these are my second level resolvents, and then I look for third level resolvents by looking at again the clauses in the base set. Now, if you recall the original proof for this illustrative example, here the darken edges is a part of the original proof. Now, one needs to understand that there are cases in which a refutation exists, but a linear input from refutation does not exist. So, this makes linear input from strategy not complete. In order to understand that, let us take an example here. So, here I have 4 clauses: Q of u or P of A, not Q of W or P of W, not Q of X or not P of X, Q of Y or not P of Y. Now, if you look for a refutation of these set of clauses, you can see that you have the set of clauses clearly unsatisfiable. The refutation tree on your right shows that I could arrive at the empty clause, and therefore, the set of clauses is clearly unsatisfiable. But then one needs to realize that I cannot have a linear input form resolution for this example. Now, for a linear input form refutation of this example, one of the parents of these empty clause that I have here need to be a member of the base set. For that to happen, one must either resolve 2 single literal clauses or 2 clauses that collapse to a single literal. Neither of these conditions are met by the base case members, and therefore, this example, even if it has a refutation, does not have a linear input form refutation, and is enough to show that linear input form strategy is not complete. However, in spite of their lack of completeness, linear input form strategy is used because of their simplicity and efficiency. Let us now focus our attention on the last of the strategies that we are discussing, which is called the ancestry filtered form strategy. In this form of refutation, each resolvent has a parent that is either in the base set or that is an ancestor of the other parent. So, this is much like the linear form strategy. Control strategy is guaranteed to produce all ancestry filtered form proofs is complete. So, completeness is preserved in ancestry filtered form strategy if the ancestors that are used are limited to marges. Now, recall that marge is a resolvent that inherits a literal each from the parent, such that that literal is collapsed to a singleton by the most general unifier. So, let us take the example that we have used for the linear input form strategy and look at the same refutation proof towards the empty clause. Now, you could see that the refutation tree on the right is produced by an ancestry filtered form strategy, because here this clause not of P of X could be considered an ancestor. While I am resolving for P A, I am looking for the parent of Q, which is P of x, and therefore the clause P of x is used as an ancestor, and this is the ancestry filtered form strategy. Now, there could be strategies that are combinations. Set of support with either linear form or ancestry filtered form is a common option. You can view that as backward reasoning from goal to sub goal to sub goal and so on. Now, occasionally combinations can be led to slower growth of the class set than with either strategy alone. One interesting point to note at this time is that the ordering strategies, of which we have only discussed one, the unit preference, can prevent the generation of large number of unneeded clauses. So, order in which resolution is performed is crucial to the efficiency of the resolution system, and therefore, the unit preference strategy has its own importance. Now, let us look at a couple of simplification strategies. We will discuss two simplification strategies, one the clause elimination and the other procedural attachment. The clause elimination strategy, the idea is to keep the number of clauses generated as small as possible without giving up completeness. So, we exploit the fact that if there is a derivation to the empty clause, there is one that does not use at least three type of clauses. One, the pure clauses; two, the tautologies; and three, the subsumed clauses. So, we could eliminate this and still be able to reach the empty clause. Procedural attachment, on the other hand, is about evaluating or interpreting a literal by attached procedures and coming down on the size of the clauses. Let us look at clause elimination first. So, we have two very important eliminations. One is the elimination of tautologies and the other is elimination by subsumption. Any clause which contains a literal and its negation, that is a tautology, may be eliminated. Now, this is because any unsatisfiable set which contains a tautology is still unsatisfiable after removing it, and conversely. So, you could eliminate tautologies to reduce down search. Elimination by subsumption is more interesting. We look for a clause Li which subsumes a clause Mi. If there exists a substitution S prime such that L of S is a subset of M. Let us take a couple of examples to understand this. Here is P of x, it subsumes Py or Qz, P of x subsumes P of A, P of x subsumes P of A or Q of z, P of x or Q of A subsumes P of f of A or Q of A or R of y. So, if you have some clauses that subsumes another clause in the set, then it can be eliminated without affecting the unsatisfiability of the rest of the state. So, these eliminations lead to substantial reduction in the number of resolutions to find refutation. Procedural attachment is another possibility, in fact a more convenient one, where the idea is to evaluate the truth value of literals rather than to include these literals or their negations in the base set. Now, here evaluation refers to interpretation of the expression with reference to a model. So, for example, I could have a expression saying equals 7, 3. Now, this can be evaluated by attaching a procedure that somehow computes or checks the equality of two numbers. So, given such a program for the above predicate, equals 7, 3 evaluates to false. So, it is possible to attach procedures to function symbols as well, and then one needs to establish connection or procedural attachment between the executable computer code and the predicate calculus expressions. How does the class set get simplified by such evaluations? There is a two-step process. If a literal in a clause evaluates to true, then the entire clause can be removed. If a literal evaluates to false, then the occurrence of just that literal in the clause can be eliminated. For example, P of x or Q of A or equals 7 comma 3 can be replaced by simply P of x or Q of A, as equals 7 comma 3 evaluates to false. This is what is procedural attachment. Other ways and means of reducing search includes a technique of using sorted logic. Now, sorted logic involves associating sorts with all terms. For example, a variable x might be a sort female, a function like mother may be of the sort person mapped to female. Then one would keep a taxonomy of sorts, like one could say woman is a subsort of person. The idea is to refuse unification between literals PT and PS if S and T are from different sorts. Now, this is under the assumption that only meaningful with respect to sorts, meaningful unifications can lead to the empty clause, and this is how sorted logic can be used to reduce down search. There is another trick of using what is called a connection graph. If I am given a set of clauses, I can pre-compute a graph with edges between any two unifiable literals of opposite polarity and label with the most general unifier. Now, resolution procedures that can be used involve selecting a link, computing a resolvent clause and inheriting links for the new clause from its input clauses. One needs to realize that there is no unification at runtime. This, if you give a bit of thought, can realize that can be seen as a state space search problem, where the idea is to find a sequence of links that ultimately produces the empty clause. Now, any techniques that I can use for improving state space search can be applied here as well. We have so far in these couple of lectures discussed knowledge representation and reasoning, argued why logic is the first choice for knowledge representation and reasoning. We have examined first order logic as a knowledge representation formalism. Now, one needs to understand that first order logic is not the only choice. However, first order logic is simple and convenient to begin with. We have looked at resolution and resolution refutation proofs. We have particularly looked at resolution derivations, symbol level operations leading to knowledge level logical interpretations. We have walked through answer extractions, and today we have covered strategies and simplifications leading to refinement in resolution to help improve search. This is where we wind up knowledge representation and reasoning. Thank you.